Hello and welcome to Sean White's Solar and Energy Storage Podcast. Hey listeners, this is a very special podcast to me. It is a podcast with one of my solar heroes. Dick Swanson is somebody that will be in the history books. I'm going to give him credit for 2 degrees Celsius, that is 3.8 degrees Fahrenheit, decrease in the planet's temperature. Dick Swanson is famous for founding SunPower, also for inventing the back contact solar cell and perhaps Swanson's Law. Dick is kind of a modest guy. He's definitely not a solar door knocker type, and you'll get to see that as you meet him in this podcast. One of the things about my podcast is I try to make the guests comfortable rather than having $3,000 worth of recording equipment in front of their face. In fact, I think if I insisted on putting $3,000 worth of recording equipment in front of Dick Swanson's face, I would have never had him on the podcast. One of the things that I like to think about is what this podcast will sound like in the future, perhaps 100 years from now or 1,000 years from now. And by then, probably by 5 years from now, we'll have the technology to turn a recording that was over a phone call into something that sounds like it's coming out of a fancy studio with $300,000 worth of recording equipment in it. One of the things that I do with most of my guests is I put them on Zoom, and there's all these other fancy podcasting types of software. And one of the things that I've noticed about being on other people's podcasts that use this fancy type of software is usually it kind of throws off the vibe. If you try to record somebody in some fancy kind of way, there's bound to be some kind of mistake, and then there's going to be stress, and then there's going to be somebody trying to troubleshoot something. And I think Zoom does a pretty good job, and everybody's familiar with it. So this podcast is also for people who have not been born yet. We want to have the historians of 2126 and hopefully even the people of the year 2060. So I'd like to think that we are fortunate enough to be alive during this historical time where people that started the solar industry are still on this planet with us, and where we get to see silicon change our lives, whether it be silicon solar cells or silicon computer chips and fancy programs. Exciting times. So here is a conversation with solar superhero Dick Swanson.
Hi, Sean.
Hey, Dick. How are you today?
Well, so far so good.
Okay.
How are you?
Oh, it's not raining, so I guess that's good. Yep.
Yeah, yesterday was absolutely gorgeous.
Yeah.
Amazing.
Yeah. Yep. And yeah, we're in California where there's no snow. It's a good thing.
Oh, that's right. You're up at Tahoe, right?
No, right now I'm in Orinda. You probably know Orinda, I guess, right?
Well, not personally, but yeah, I've been through there, right? Yeah.
Yeah, but I live in a little place called Canyon, where it's a piece of property that's 42 acres. It's been in my family pretty much since the 1850s.
Oh, cool.
Yeah, my great-great-grandparents immigrated there, 4 of them, and my uncle sold it 11 years ago, and I bought it back a year ago.
Oh, my God.
And
oh, man.
Yeah, and it's like a little community. It's like dirt roads, and I'm making a solar.
So there's multiple families there? Is that
Yeah, there's actually about 30 people living on the property.
Oh, wow.
Yeah.
Sounds like a sort of a prepper community or something like that.
Yeah, kind of a little bit more hippie than that.
Yeah, okay.
Great. Yeah, well, thanks so much for agreeing to talk to me and all that. And for like the way I found you was you signed up for a joint membership for NorCal Solar, which is a division of ACES. It used to be called Northern California Solar Energy Association, but they changed it to NorCal Solar. It's actually sort of still is called the old name. And you probably know more about that than I do. I should say the beginnings or like the earlier days of the different solar organizations.
Well, I am old, but the solar organizations actually predate me, you know. When was ACES formed?
1954. Yeah, they had a meeting.
54.
Yeah,
right.
54 in Arizona. Yeah.
In Arizona at the time of that, they had a special conference in Arizona. They brought people together and that sort of thing.
Yeah, and it was more solar thermal back then. It was like solar cookers and stuff.
Yeah. Absolutely, yeah. Although I believe they did invite Gerald Pearson to give a presentation, who was, fresh off and discovering the silicon solar cell at that.
Oh, who was that?
Gerald Pearson.
Gerald Pearson. Okay.
Yeah.
And so, who's Gerald Pearson?
Well, the original silicon solar cell was discovered, I guess is the right terminology, at Bell Laboratories.
Uh-huh.
And Gerald was the person he was working there, and he was the person that first noticed this abnormally high current in what was intended to be a silicon diode.
Huh.
And he collaborated closely with Daryl Chafin and Ardeen at Bell, and they kind of made some samples, and Bell Labs had a big splash about it, this is the new way we're going to power the world, which created a lot of press and that sort of thing. But it turns out it was like, I don't know if you've read John Perlin's books. He's sort of
he's been on the podcast too. Yeah.
Mm-hmm. Oh, has he?
Yeah.
Great. Yeah, mm-hmm. yeah. But I learned from his books that there had been a series of these flashy announcements going back to the beginning of the 1900s that, with the discovery of the selenium solar cell, that was going to change the world. And so let's put it this way, a considerable number of premature shots at it.
Maybe until you came along.
Not at all. But really set the hook, I think, got people going was the energy crisis of 73. And, we all spent a lot of time standing in line, waiting for gas, and had time to think about these things. And it seems to me that, at least, I was just a young researcher at the time, but it seems to me that was the moment that people realized energy was important and not just something that came out of a plug on the wall automatically. And, maybe we should look into it. And, things like EPRI was formed, Electric Power Research Institute, which was created largely because suddenly the country realized that all of the energy research was done within the supplier community to the utilities. The General Electric did its own research, Westinghouse did its own research, but there was no coordinated national look at energy issues. And so there's a realization that we needed something more comprehensive, if you will. So the Electric Power Research Institute was created by some sort of act. I know that the methodology that was put together to allow that, which at first blush it would appear that the utility members were conspiring in anti-trade activity, the methodology was sort of laid out the groundwork on how they would interface with each other was groundbreaking and was used, for example, to set up the chip industry analog of that many years later when Intel and others got together and said we needed to set roadmaps for the industry and that sort of thing. So anyway, EPRI was formed, and the Atomic Energy Commission started looking into it. There was a lot of confusion in the early days about within the federal government where such activities should be centered. And so this sort of, forced a call of the cards, if you will. And so we had NASA, of course, interested in solar cells, and we had the Atomic Energy Commission interested in energy issues, and we had the National Science Foundation thinking they should help. And so, all these agencies kind of started interacting and working together to hammer out a coherent strategy, if you will, for the U.S. and put together a program that, in my view, attracted an incredible group of people to come sort of stake their careers, if you will, on developing solar cells, and created an environment that was, I just, in retrospect, feel so lucky to have stumbled into, where you had all of these really dedicated, brilliant people working together towards a common goal, each on his or her own idea, but all working towards the same goal, which, by the way, at the time was centered around we're running out of fossil fuels. We need to find an alternative. That didn't happen. B, nuclear power is too dangerous and we're going to blow up the world. So we need an alternative to that. That didn't happen. So all of the sort of foundational structure that brought everybody together to work on this turned out, in sort of full light of dawn to have been quite different than we expected. And it's kind of hard to imagine now, but the concept of global warming, for example, basically didn't exist. I mean, there were scientists that talked about it, I guess, but it wasn't part of the dialogue. If you look at all these founding documents, the idea of combating global warming doesn't really get mentioned. Mm-hmm. But it's good we did it. Given that we now know that if we burned all the fossil fuels that we now can recover, we're going to basically fry the planet, So there's been sort of a lot of fortuitous events that were not obvious at the time that all kind of worked together to get us to where we are today.
Mm-hmm. One thing I've thought about too is when we talk about CO2 in the atmosphere and warming the planet and all that stuff, you could make the numbers, you could do a calculation and it would be a very small number, 10 to the negative something, where like even an individual solar module being installed could have an effect on the temperature of the planet. It would be a very super, super small effect. And I would like to give you credit for a much bigger effect on keeping the planet cool. With all the work you've done, have you ever thought of that? Like what temperature change the planet would have if it wasn't for you? I mean, I know, with SunPower, some of the biggest systems in the world have been SunPower systems. Like sometimes it's been the number one biggest PV system in the world has been a SunPower system.
At one point that was true, yes.
Yeah. And there's bigger systems and things. And then with your technology, people have copied you. And now, I guess I think the patent expired for the back contact solar cells. So now people are copying you. But how do you even feel about that? Like people copying you? It's good for the planet, I guess.
Well, first off, I am 80 years old, so it's like looking back, and I think it's wonderful. One thing that does sort of pop up in the whole thing, if you look at the types of cells that people are exploring right now and looking towards the future, there's sort of three main types, if you will. There's the HIT cell, the amorphous silicon passivated cell, the IBC cell, and the TOPCon type cell. Mm-hmm. And those all came out of the original work, all came out of university labs. Okay. Mm-hmm. The HIT cell in Japan, and the TOPCon cells in Europe at Freiburg and in University of New South Wales, and the IBC cell at Stanford. So,
and that's you. You're the inventor of it. The IBC back contact.
Yeah, I mean, the IBC, the idea of putting all the contacts on the back of the cell predates me. In fact, there's another group I haven't mentioned, which was Dick Swanson's group at at Purdue University. And Dick was one of the early workers in this field that came at the time I mentioned, and he had been working on germanium cells, not silicon, but germanium, which has a lower band gap than silicon. And the germanium cells were intended for using what came to be called TPV, thermophotovoltaics, which is the conversion of radiant energy from a hot surface other than the sun into electricity. And so he recognized when you have high intensity, high fluxes of energy, and therefore a lot of current to deal with in the cell per unit area, a lot of current per unit area to deal with, that it was advantageous to have all the contacts on the back. So the idea of putting all the contacts on the back of the cell was in the air already, and Dick invented the term IBC for interdigitated back contact. Now, what the Stanford group, my group, sort of did is say, hey, why don't we make these in silicon and use them in concentrating systems? And in fact, now that I get my brain in gear, we actually decided to use TPV approach at first. And the reason for that was that I had gotten a fellowship from IBM to study solar energy. I just finished my research at Stanford, which was in the chip field, CMOS. And I was asked by IBM if I wanted a postdoctoral fellow. They did one every year at Stanford. And would I apply for it? And I said, sure. And when they came to interview me, the IBM representative said, so if we give you this, what are you going to work on? And I said, well, I'm going to work on solar energy. And he said, well, IBM has no interest in that. So he left, and I thought, I'm not going to get that fellowship. Well, strangely enough, I did. And so I had this period of a year with no boss, if you will, and no reports to write, no nothing to do except think about how to make solar energy practical. And I began that quest by looking at what it would cost, I thought, to build a system. And, these are very early looks at that. But one conclusion that I came to was that the efficiency had to be fairly high in order to just pay for the things that you knew you were going to have, like foundations and mounting structures and glass and that sort of thing. And when I looked around, the numbers that I was getting were that the efficiency should be much higher than what anybody was thinking at the time would be practical from regular solar cells. Thin film, like amorphous silicon cells were 5% efficient or something, 7% maybe by then. And crystalline silicon cells were 12%. And so I kind of came to the conclusion that wasn't going to happen, that we needed something completely different. And that's when I came across the TPV work.
TPV.
That started the thermal photovoltaics, which is where you have this hot surface.
Oh. And
that work began at MIT, and Dick Swanson had taken it up at Purdue with germanium cells. And it's interesting that sideline, you probably don't really care, but Purdue was like the center of excellence for germanium semiconductors at that time. They had been part of the World War II effort to develop detectors or mixers for radar systems using semiconductors, and germanium was one of the preferred materials. And so Purdue had in-house capabilities in germanium, which was unusual. And so they were in a position to make these TPV cells, and you wanted a lower band gap than silicon because the temperature of the hot surface was going to be less than that of the sun, right? So, so the energy of the photons coming off was lower, and so a smaller band gap was advantageous. So they worked on that.
What temperature are we talking about? Is it concentrated or?
Yeah. Okay. So this would be very high temperatures. So the original Purdue work was envisioned a gas-fired burner, like like almost think of a Coleman lantern or something, where you're heating something to a very high temperature and then surrounding that with these solar cells and making a generator out of it. And you might imagine that this generator would be quite quiet, and so you might imagine that elements in the military would think, gee, that would be something interesting to work on, and so they did. And TPV kind of has a long history that we don't want to spend any time on now, but it kept resurrecting itself almost like locusts. So it had died out, and then I came across it, thought, gee, maybe that's the way to get high efficiency. With a concentrating system, you concentrate sunlight, and then you heat something up till it's glowing, and then you put solar cells around that. And the compelling thing about TPV conversion is that in a sort of theoretical abstract sense, in an idealized case, it's an ideal heat engine, and therefore it has the energy conversion efficiency, the maximum possible energy conversion efficiency for converting heat into electricity with a given source temperature, so-called Carnot limit. And so, that could be very high, like 80% or something at the temperatures we're talking about. So TPV had this sort of draw, and every time somebody looked at it, they ended up with something that was more like 10% or something. It was like, but the theoretical limit was 80%. So, we're great righteous researchers, surely we can breach that, and nobody managed to pull that off. But so I started what might be thought of as the second wave of TPV, and it was in that period that we said, let's try and make a silicon IBC cell. So the thing was that we didn't have any capability to make germanium devices, which would have been probably better for TPV. So we said, well, we'll just make them out of silicon and see what happens. And so that was the potential efficiency of that, high efficiency potential that you could sort of make a PowerPoint, but today you make a PowerPoint presentation saying how great this is what enticed EPRI to begin funding me. And that because they had come to the same conclusion independently, that low efficiency panels just would not fly, if you will, in a utility environment and make competitive electricity, so that sort of thing. So we had our media minds, and they began a long-term relationship with EPRI that was seminal in getting us going, including early funding at SunPower Corporation.
That's interesting. Yeah.
Yeah. Well, halfway through this, I suddenly realized that TPV was just plain bad idea. The killer aspect of it was that we couldn't find any radiator materials that would operate at these temperatures we were running that didn't evaporate slowly and get on the front of the cell and kill the whole system. So we said, okay, let's just pick the radiator out and get into concentrating PV systems. So we transitioned to concentrating PV systems. And that was the first major pivot that I made, was to admit that TPV was not going to cut it. And it was a very painful realization after spending 5 years pursuing it and switching to concentrating systems. And at that time, you have to realize that in the community, electric solar cell community, the established truth was that crystalline silicon flat plate was hopeless. That you could never possibly make a crystalline silicon wafer solar panel that was even close to the cost effective. And so everybody said, okay, something else, we got to do something else. And most of that something else was the thin film program. So when this is all happening, the thin film group is thin film activity is starting to develop. We had some at Stanford under Richard Bugh. And I looked, so the conventional wisdom was that if you want to work on solar cells, you better work on thin film solar cells. And, that when I looked at it, it was very material science oriented. And my whole experience was working with silicon. I knew silicon material and how to process it. And we had a silicon integrated circuit lab at Stanford. At the time, it was really the only one, significant one in a university environment. But I couldn't figure out how to do the thin film stuff. It was real material science, these compound materials, oxide semiconductors and sulfur glucosides and that sort of thing was all kind of a mysterious black box magic to me, not being a material scientist. And so, okay, well, I'm going to do concentrating systems because you can use silicon, and I know how to make silicon solar cells. And so that's the direction I went. And so we finally settled on doing concentrating PV systems. And that was the sort of other horse in the race from the point of view of the Department of Energy. You had thin films and you had concentrators. And then there was a sort of afterthought on wafered silicon, which, my recollection of the time is that the DOE said, well, we've got a couple of manufacturers making wafered silicon solar cells, Arco Solar at the time and SolarX, and we should do something to help them out from a research point of view. So let's start a flat plate silicon solar array program, which was managed by JPL. But if you look at the old documents, it says things like, this will be obsolete in 5 years. So this program has just sort of helped these companies survive until thin films come on, right? Or concentrating systems. And it's sort of the irony of the whole thing is that the modern concept of a solar module with glass on the front, et cetera, came out of that program, the JPL program. And so that sort of stopgap measure ended up being the main avenue for the future. Meanwhile, there was a group of us doing concentrators and then a much bigger group doing thin films. And in fact, SunPower was formed to do concentrators. So you asked about the IBC cells. So our contribution was to figure out how to make it work, basically. I mean, if you looked at early IBC cells, they were very stunted in their performance capabilities, and it was largely because the contacts on the back covered the entire back surface, either N or P, alternating N or P, but
negative, positive,
yeah, and negative and positive on fingers on the back, like interdigitated combs, if you will. And at the time, it wasn't realized that it was the metal touching the silicon that was limiting the performance. And so it turns out that metals are just not very good semiconductors. They're not semiconductors at all. And so where they touch the silicon, they kind of poison the silicon at that point, sucking out minority carriers that you would want to come out the other contact. So as research really developed, we started realizing where the loss mechanisms in regular solar cells were. And the main contribution that the Stanford group did is we went to what became to be called the point contact. So when we shrunk the metal semiconductor contact areas to a small fraction, like 1% of the backside, instead of essentially all of the backside of the cell. And so you can sort of think of the progress in solar cell efficiencies since then as ways to reduce the negative impact of having the metal contact the semiconductor. In one case, you have an amorphous silicon layer there that separates them, and in our case, we had little tiny point contacts to minimize the area. Now as TOPCon cells and PERC cells use the same idea, and now TOPCon cells do the same thing. But one of the important realizations in the development of the technology that occurred in the late 70s was this realization that it's the metal contact to silicon that is the reason that commercial solar cells are only 12% efficient, when we knew that the thermodynamic limit, the so-called Shockley-Queisser limit, was more like 30% or so. So it, went off and started working on that. It was kind of fun because it was good university activity, researching these things. But within the conventional solar industry, I think many of us, we always viewed as sort of lost in the clouds working on impractical. Yeah. It's nice you can build these high efficiency solar cells, but they're impossible to make on a production basis. And so it's kind of a toy. And I remember Martin Green once defending that at a conference when he said, well, it's kind of nice to know what the limits are anyway, even though these are not manufacturable. So it's with some smiling pleasure that I think back and realize that those of us that were working on those, that's how the solar cells are actually made. So that's one thing that, you asked about how I felt, and that's one thing I feel good about.
Great. Yeah. In addition to this podcast being brought to you by Shawn White's Solar and Energy Storage Podcast, it is brought to you by Intellectual Curiosity. Let's see. So we were talking about 1954, and that's when the American Solar Energy Society was founded, which was pretty much founded at the same time as the International Solar Energy Society, and also the same time that Bell Labs came out with, I guess maybe the first solar module, solar panel. Did you?
Solar cell, right? The actual panels were a little bit later.
Did you ever see one of those? Like I see these pictures of the Bell Labs advertisement, and they called it the Bell Solar Battery.
Yeah.
I've never seen one of those in person. I imagine maybe you have, or maybe they didn't make many.
Well, Gerald Pearson, who was one of the co-inventors, came to Stanford and became a professor there. And so I knew him, and he had one of those in his office, prominently displayed. So yes, I've seen it. They're like 3/4 inch diameter ingots and something on that order, which was the biggest single crystal ingot you could grow at that time. And they were embedded in a dielectric liquid between two plexiglass plates. So that's how the modules were made. These cells were sort of soldered together. I don't remember how many were in there, like 10 or something, but between two plexiglass plates, and then that was filled with some liquid. I'm not sure what, probably a silicone oil, and put in that case, and that was the panel.
Do you think any of those exist still?
Oh yeah, they do. In fact, I know that a friend of mine at Stanford, Jim Harris, has Gerald Pearson's panel.
Oh yeah.
So I think they made a handful of those early ones, and that's the only one I know where it is. Jim Harris also has one of the transistor. You've probably seen that picture of the little triangular shaped piece of plastic with whiskers, like paper clips sticking off the top, the first transistor from 1948.
So is that a solar cell also, or just a transistor?
No, it was a transistor. So 1948 was the first transistor. And so it was the same organization that did that. And Jim Harris actually has one of those transistors too.
Oh, wow.
So he's got quite a collection. But yeah, so they made the transistor. And in fact, I've been researching a little bit of this period for a paper I'm writing. And it's fascinating in that what I didn't know until quite recently is that both silicon and germanium were not known to be semiconductors at all prior to World War II. Huh. And all of the only semiconductors that were practically unknown and well researched were selenium and copper oxide. And then, so the people kind of understood what a semiconductor was, but they didn't have much theory to back it up about what. And so it wasn't realized that silicon and germanium were semiconductors. And then as part of the war research effort, they discovered that essentially at Bell Labs. And with some university partners, one was Purdue, and where they had worked on germanium, and the other was Pennsylvania, Penn State, I guess, or University of Pennsylvania, not sure which, where Fred Seitz was. And they were all working together as part of the war effort, and it was highly classified. So nobody outside of Bell Labs and a few people in these other organizations even knew that silicon was a semiconductor, let alone how to work with it. And so they perfected all of that, how to dope it, everything. Like, the things we think of today as sort of standard stuff like N and P dopants and, yada, yada. That was unknown and all developed in the secret war effort. And then when the war ended, a lot of that classified stuff took a long time to get declassified. So, for example, Seitz wrote a review of semiconductors, I think in 1947, if memory, that covered the field. And in there, he didn't even mention silicon. So it was still classified, obviously, at that point.
Maybe we should have kept it a secret, huh? They would have never figured it. We should have kept it a secret.
I don't think so. It was, in fact, I misspoke a little bit because there was a group in Russia under Yoffe and that did it, and there was that had realized this, and a researcher there published a lot of the original papers. His name was Davidoff, but a lot of that literature was not known in the West. And anyway, it's just a huge mishmash of complications. But one wonders, at first you might say, gee, why did the transistor in 1948 come out of Bell Labs? Well, it's the only place that knew how to make this stuff and knew it even work. And so after they made the original transistor, there was a lot of effort to make single crystals of semiconductors. And because the original stuff was done by sort of probing around on little polycrystalline samples, if you will. And so at Bell Labs, they developed ways to grow single crystals, ingots, and admittedly they were only 1/2 inch to 3/4 inch in diameter, and they're sort of the size of a cigar, compared to today's ingots, which are, 12 inches in diameter and 30 feet long or something. Jeez. But they were single crystals, and that was at Bell Labs. And so they had access to this. And then another missing link in the whole thing was what to do with these single crystals after you sawed them out into wafers. And at Bell Labs developed this diffusion technique to diffuse dopants into the surface. And so they were recent, and a guy named Fuller was working on that. And so he had made the first diffused diode with an N-type substrate and a P-type diffusion layer on the top. And he sort of took it over to Gerald Pearson and said, what do you make of this? And it was then that he tested it in his lab, but of course the window was open and light was coming in, and he went, whoa.
So it was an accident.
It was an accident. Absolutely. It was, yeah. And they said, gee, maybe.
So
something here.
If it wasn't a sunny day or his office was in a dark place under a tree.
Right. The accident would have happened another, later, but not that much later, I'm sure. Because it was clearly in the wind. And then Bell disseminated all the semiconductor knowledge that they had as part of a government agreement and signed up the companies to look at it. And that sort of spawned the modern semiconductor And, Texas Instruments took a license, even though they didn't, they were making oil equipment for oil drilling or something like that. And General Electric and all those major companies the labs taught a course, this is a semiconductor, this is N dopant, this is P dopant, that kind of thing.
Great. Another thing that you were talking about was really interesting to me is when you talked about TPV, thermal PV, and I've heard of something called PVT, PV thermal, and they're usually talking about heating up water when they're doing silicon solar, making electricity at the same time. And you were talking about concentrating light onto something that get it so hot that it glows. And I guess that would be a better wavelength of light to be more efficient.
Yeah, there was, right. So this is completely different than PVT, where you're using the waste heat off a cell that's being illuminated by the sun, for heating or something like that. The thing that makes TPV, or thermophotovoltaics, where you're illuminating the cell from a hot radiating surface, it makes it efficient is, you don't have so many photons with a lot of extra energy that's wasted when it hits the cell, but you do have a lot of low energy photons that don't have enough energy to be absorbed in the silicon and excite electrons and holes. But what you can do in that case is you can reflect those back to the radiator.
Oh.
And that came to be called photon recycling. Sort of think of it like a photon comes off a radiator, it comes out, it doesn't have enough energy to make the solar cell generate current, so it gets recycled back for another shot. Maybe next time it'll come out with enough energy.
Okay, right. That's kind of...
Yeah, it was very, it's sort of very similar in a way to, I don't know if you've followed any of this, but like Stirling engines. I mean, they have a long history, invented in the 1800s and realized by the time that Carnot came, that all the thermodynamics got worked out, that they had a theoretical limit of the Carnot limit. A Stirling engine is theoretically capable of the highest possible efficiency. So that to this day attracts people. It's like, geez, wow, man,
And so a Stirling engine is some sort of steam engine, right? Is that?
Well, Stirling engine is a heat engine that converts heat into work or electricity if you want. And so the heat source is kind of agnostic. It could be from steam or hot air. Usually all the early work in these types of engines were with hot air because steam engines had gotten a bad rap in that they tended to blow up. And so there was a lot of interest in what were called air engines, like Ericsson, the famous guy that built the first engine-powered boat, that you learn about as a child in school because he was an American, built air engines. And so, this was a way to avoid the danger of a steam engine. And then shortly thereafter, the material scientists, again, those guys figured out how to make boilers that didn't blow up. So took the steam out of working on air engines, if you will. But people work on them to this day. I mean, Stirling engines, it has a very long and interesting history. The cycle is used a lot for cryocooling. For example, in semiconductor manufacturing, the vacuum pumps are often on cryo pumps, and they work by cooling a surface down to very, very low temperatures, close to absolute zero, where the gases all condense on that surface. And that little pump is actually a Stirling engine running backwards. Yeah, so... And we're kind of getting a little off.
Okay, no, all that's
topic here. I realize.
I like it. No, we don't have any particular topic we have to talk about. This is all very interesting. One of the things that when you were talking about TPV, it reminded me of something that Bill Brooks was telling me, that his idea for a furnace that has to have electricity to go in the winter when the tree falls over the power line is to put some solar cells in the furnace to power the fan, so you don't need electricity from the grid. I thought that was kind of interesting.
Yeah, that's called TPV. Right?
Yeah. And I don't know if anybody's even doing that. I thought maybe he just had an invention or something. But so I guess it gets a better wavelength of light that's more efficient too. Is that?
Yeah, and then this idea of reflecting the light back. I mean, if you don't care about the efficiency, like you're just trying to make a fan go, that's one thing. But if you do care about the efficiency, you're reflecting the light back to the source. Now, you can do that with a concentrating PV system, you can, in fact, a perfect concentrator, the light comes in from the sun, goes onto the cell, and if it bounces off the cell, where does it go? It goes back to the sun.
Yeah.
Now,
heats that sun up.
Right. So it turns out, since we're not paying for heating the sun, it's kind of like a point, right? But in a TPV system where you're actually paying to heat the hot surface, yeah, that's a good thing.
And I guess with a furnace, you're just trying to burn stuff to make heat anyway, so it doesn't really matter if it's turning into waste heat. It's not really wasted because that's the whole idea.
Exactly.
Yep.
Exactly. Yeah.
That's pretty nice. So one of the things that you're kind of famous for, and I know that in the past you've kind of denied that you should be famous for it, that they call it Swanson's Law.
Right.
And when you kind of came up with that idea and applied it to solar, did you have any idea where we would be now? Like the least expensive form of energy in the world, pretty much?
Well, no, nobody did. But I didn't come up with that idea. When the program got going, of course, the question when the solar research program got going worldwide, in 1973, like I mentioned, the question is, where can we go efficiency-wise, and what efficiency is needed, and how to get there? And so a lot of work went into that. And one of the first director of the PV program at what became the Department of Energy was a guy named Paul Maycock. Paul had come from Texas Instruments, which of course was early in transistors and taken that early Bell Labs license. But he revealed how at Texas Instruments, they would use a so-called learning curve for a cost projection. The learning curve idea had been developed, as far as I know, at least put to practice during World War II in the manufacture of things like bombers. And what people had noticed is that each bomber you made cost less than the one before because you learned how to do it more expeditiously, right? And what the sort of surprising thing was that when people plotted cost versus number of units, bombers originally or transistors later on, that if you plotted that on a plot where the x-axis was the cumulative number, starting with 1, the first one, and the vertical axis was a logarithmic plot, that you got a straight line. And so this was called the learning curve. And what you would do is just say, okay, we have this data, so why don't we just put a ruler on it, draw the line for lots of number of units, and that should give us an idea what the cost would be when we produced 1 million units or whatever, right? And so apparently Texas Instruments, Paul may have told me this story over a glass of beer or something like that, I'm not sure, but apparently Texas Instruments was using this observation to forward price. So they would get an order for chips, and they would quote a number below their manufacturing cost and win the contract. And they would quote below the manufacturing cost on the assumption that as they made more of them, the cost would come down. And it turns out that worked. This forward pricing idea worked. And, Texas Instruments became a major producer of chips. And so Paul brought that same idea to DOE and plotted probably the first learning curve for solar modules, starting with solar cells for satellites, which were like $1,000 a watt. And going down the first commercial modules, which at the time were started at about $30 a watt and rapidly got down to about $10 a watt. Now, this is in dollars at the time. So, and one of the things you have to, this is $1973. So there'd be much more today at that same price. So one of the things you have to do on a learning curve that spans many years is adjust everything for inflation, a CPI, if you will. But in any case, he was drawing this line. And it's interesting that, those early lines basically said that if you drew them long enough, that when we got to terawatt scales, we would be at 10 cents a watt or something like that for the panel. First off, the idea of a terawatt was so, when we'd only produced a couple hundred kilowatts in the history of the industry, was so far out there that you couldn't. And secondly, no, I don't think anybody really took that seriously, that you could extend this thing through, factors of a million, if you will, in costs or something. So it wasn't taken seriously. And in fact, it's kind of sad that DOE didn't take it more seriously, because they still were sort of, in this mindset that we need a breakthrough. We can't just turn the crank on silicon solar cells and expect them to come down, because after all, they don't meet our cost goals until we get to a terawatt, and that's ridiculous. So we need a breakthrough. And of course, if you look at it's kind of amusing to look at the graphs that were produced by DOE and presented at conferences and stuff, where they had the costs come down dramatically due to a breakthrough. Okay. But even with that, they got the cost down to the 50 cent a watt level, by 1995 or something. So we hit that.
Oh, for the cell or something.
For the module.
For the module.
Yeah. And we hit that point actually about 20 years late. So, 20 years later. So, from my perspective, it's just like a typical schedule slip, We were 20 years late meeting the goals, but we did it. So that was the origin of the learning curve. And, there was usually a learning curve presented at most conferences, and I had nothing to do with it. And the reason my name gets stuck to it is kind of embarrassing, in that I started using this concept to talk to anybody that would listen to me, mostly regulators and politicians, to present the idea that costs are coming down. We're going to figure this out. Trust us. They've been coming down for a long time, and they're going to keep coming down. And so therefore, the fact that you're supporting us with all this government support, both at the research and system level support, it's not like we're asking for a perpetual handout at the trough. We're going to work through this, and then you're going to be able to stop the support. And that, the idea was to give legislators and whatnot sort of some reason to keep dumping money into this, which, a lot of people thought was a will-o'-the-wisp, that you're never going to get there. Why are you wasting money on this? That kind of thing. And so I was talking a lot about it. And then a lot. And then I gave a talk to a bunch of journalists. I won't say who, just to protect the innocent here, but they came out after I got an award, and I gave a talk to them, and they came out with a statement and called it Swanson's Law. Like, that's the first time they'd seen it, right? And so they assumed, I guess, that somehow it was my idea. So it was really embarrassing, in the sense, I've got these people, hey, Swanson, what the heck is this? What are you talking about?
I think we could tell that you wouldn't make a good door-to-door solar salesperson, because then you would be claiming that it was yours, or a politician.
Right. I wouldn't make a good salesperson for
Yeah.
anything.
Do you think that the same cost curve applies to batteries?
Yeah. Yeah. And it's kind of interesting in that one of the objections to the learning curve is that, first off, let me say that as far as I know, nobody knows why it works. Nobody knows why, except that generally when you plot logs of things, they tend to be a straighter line than if you didn't plot it on a log plot. But other than that, why it works, why it extrapolated through orders of magnitude to hit today is kind of a mystery. As far as I know, there's no theoretical basis for it, right? But what was your question? All of a sudden, I lost the thread.
I don't know. I think you're going in the right direction.
Yeah. So,
do you think there's a limit? I know that,
that was it.
Say with Moore's law, everybody thinks, we're reaching the limit next year, and then it never happens.
And then they always say, never mind. Right? Yeah. So the same thing happened. Yeah, it happened here. So the naysayers would say, there's a limit in the cost of glass. Come on, you're going to eventually hit, there's a limit in this. All these parts have a materials limit. And the argument was that when you hit those limits and you started to buy glass, it's a commodity that is, has a broad application, and their little solar cell is not going to affect the price of glass, right? Yeah. And so, of course, there's a limit. The thing is that we just blew through all of this. Yeah. And part of the reason, there's many reasons for that, but part of the reason is that all of the commodities actually have their own learning curve. So, for example, you take the steel in the foundations and support structures of a power plant. That steel is considerably less expensive than the steel would have been when we started looking at this in 1973. And it's like, duh, of course, because the steel makers, their furnaces are getting more efficient. They're getting more efficient. They're having their own learning curve. Now, they didn't start with Unit 1 in 1973 like we did, 1954 maybe. They started with Unit 1 in 1820 or something, right? So they're further down, but they're still marching down the learning curve. And so you couldn't imagine building today's power plants with, LCOEs under 5 cents kilowatt hour using steel that costs the same as it did in 1973. And then, okay, steel's cost less. Also, you're constantly trying to figure out how to get less steel in there, right? I mean, that the amount of steel per watt, if you will, is just, susceptible to just lots of people just beating on it, little bits here and there and there. Those keep going down the learning curve. So the balance of systems component has its own learning curve in PV, and it's very real. Like, for example, the balance of system cost for Rancho Seco, which was one of the very early large 1 megawatt installations near Sacramento. I'm trying to remember, but I believe in current dollars, it was $600 per square meter. Okay. So today, the balance of system cost is less than a tenth that. And the balance of system is nothing but standard construction materials, steel and concrete and whatnot. So all these things have their learning. And so you put the global thing together, they all come in. Glass is one of the most incredible ones in that, like, the cost of glass for PV panels is, well, let's put it this way. The whole panel today costs less than if you were to go to Lowe's Hardware and buy a window glass.
Isn't that crazy?
Yeah. And you say, well, now, how can it be? Because the panel's got glass in it.
Yeah.
Well, you're not contemplating is that there's whole cities built around this now that make solar modules, and they produce glass specially for solar modules in huge factories. It just comes right out of these factories, makes glass for solar modules. Doesn't have to go through some kind of distributor supply chain and get shipped all around, So the scale that PV has become, I think, enabled cost reductions that none of us in the early days appreciated the strength of, if you will, right? The impact of that. And, it's sort of like, when I think you could see the change in the industry when it's starting to get through a couple of megawatts per year production levels like at ARCO, and when larger firms got involved, especially in Asia, they brought a different mindset to it where, like in a small PV company, you have somebody, you basically say to some engineer, hey, why don't you find some good glass for our modules? And the poor engineers call up, oh, how much is glass? It's not their specialty, and then you go to a modern situation where you have like a trading desk, with monitors over it, and you have, glass procurement is a huge deal. So that sort of leap of vision was hard for those of us engineers and stuff who were sort of stuck, trying to make the cells work. We didn't anticipate that. And fortunately, it's amazing what's happening. It just blows you away.
Perhaps in the future, the costs can come down because a lot of the costs are based on energy, and with solar bringing down the price of energy.
That's a great.
And also the silicon computer chip too, automating things.
Yeah. And it ties right into one of the objections to solar, which from the pundits that don't think it's practical, they always, for years, we had to deal with the fact that there was this common wisdom almost that solar cells never produced as much energy in their life as it took to make them. And, that sort of tied back to somebody that said something like that in a popular magazine like Scientific American. And so, which might have been true in 1960,
Well, it's also true when you install them indoors.
Yeah,
or,
indoors, right.
Or if it's on a call box or a parking meter or something, maybe.
Right. So there, the value is created is not essentially that, but by eliminating all the wiring, the conduits and stuff like that.
Yeah.
So, yeah, I think the understanding of how this could play out was just not fully appreciated. And that's why, those in the industry are just going, gosh, I can't believe this. How did this happen?
Yeah, even for my much shorter time in the industry, I know we would have never imagined how inexpensive it would be right now.
Yeah. Right. And so, it creates whole problems that we didn't spend, a minute worrying about, grid interaction, grid stability, land use. I don't remember, back in the 70s, everyone went, gee, this is going to use valuable land. Where are we going to, that kind of thing. But so it's been quite a saga, really.
Great. We interrupt you for a very important announcement. Shaun White's Solar and Energy Storage Podcast has been brought to you by Shaun White's Solar and Energy Storage Podcast. That's right, Shaun White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSEAN, that's Solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show. Well, I remember too, I was talking to you last week, and you mentioned something about a run-in with somebody named Elon. Maybe you could talk about that. It was kind of interesting.
Yeah, well, yeah. I mean, I was talking about how when we were in one of our interminable fundraising activities in the late 1990s, Elon came to take a look at SunPower as a potential investment. This is before testing, of course, and we gave him a pitch, which we were proud of, although it wasn't terribly successful in getting funding. But he, halfway through the pitch, got up and said, well, you guys are not thinking big enough. Turned around and walked out. And, we're all sitting around the conference table going, whoa, what was that? And of course, much later we learned what he meant by thinking big. I sometimes wonder what would have gone differently had he had decided to try and make us think big, but he didn't.
And he still funded you, right? He
never funded us.
Oh, I thought you said he wrote a check or something like that.
Oh, that was Cypress Semiconductor. So that was after this. We're looking for funds again, and this was in 2000. And I had a friend that said, who was working at a local semiconductor company called Cypress Semiconductor, and he said, well, you should pitch TJ Rogers, who's the CEO of Cypress, and he might be interested in this. And so, it was like we did, and it was, I didn't think too much of it because we, been doing these on a regular basis and not gotten much traction. And, he just understood it right from the get-go. And being a silicon manufacturer, I think he realized that they understood how to process wafers and make chips, and that they could apply that knowledge to solar cells. And, he also had a libertarian streak, and I think he kind of enjoyed the idea of sort of sticking it to the utilities, if you will. So anyway, there was a meeting of, both political and technical capabilities there. And then I told him that we were about to have to lay off a bunch of people because we running out of money. And he said, how much do you need? And I said, well, we need about, I need payroll, we need $750,000. So he whipped out his checkbook and wrote me a check right there.
Oh, great. Okay. Well,
yeah. So, and that started a relationship with Cypress that, lasted for a long time. And Cypress really did create the modern SunPower manufacturer. And we, he looked at us and said, you guys are a bunch of academics and you don't know anything about manufacturing, and therefore I want you to make a production line. By the way, I had pitched him on the idea of concentrators, and it wasn't until sometime later, like a year later, that we all got together at SunPower and said, this concentrating CPV thing is just not getting traction. It's not going anywhere. We're going to have to go to flat plates. So that was the second major pivot in my career, was to go from concentrated PV to flat plates. And of course, we had been watching the flat plate industry all along in the 90s and starting to get traction, but we couldn't figure out how to play in it. We were paying more per wafer for our wafers to make cells than ARCO was selling complete panels.
Uh-huh.
So it was sort of like, how do you do this math, And we couldn't figure out how to do it. And then when we got teamed up with Cypress, they said, oh, well, here's how you do it. It's like you do volume manufacturing and you distribute you become a major customer of the wafer companies and you get your wafer price down and, all of that. Sort of early intimations of the whole thing about volumes bringing prices down. He and Cypress opened our eyes to it, and he said, we're going to build a pilot line now. You built these cells for Helios, the solar-powered airplane. You built cells for Honda. They won this race across Australia. And you do make the highest efficiency cells, but if you had talked to somebody at that point in the industry about SunPower, they would say, yeah, well, they make these little handmade jewel solar cells that are very efficient, but it's impractical from a manufacturing point of view. So it was Cypress that came in and said, okay, let's apply a modern chip making methodology to your thing. We're going to send all your engineers to our factory we have in Texas. They're going to get, embedded with the DNA of manufacturing and how you do it. And by God, it worked, and we opened a big factory in Manila.
Oh, I've been there. Yeah.
Oh, have you?
Yeah. I had somebody take my class, and then I went and visited him, and he took me to the place over there in the Philippines. Yeah.
Okay. Yeah. And so, that was certainly, I think at the time when we were doing pitches, as we've always been doing pitches, for many, but one of the things we pointed out is that there was only one wafer manufacturer, solar module manufacturer in the early 2000s that had chip operation going, and that was Sharp. And so Sharp made both conventional flat plate solar modules, and they made semiconductor chips. And we felt that there was a synergy between the know-how in the chip manufacturing sector that could be ported over into the solar cell manufacturing side. And that's certainly true. I mean, because the chip industry, had become extremely competitive, and it just, had been 50 years of just beating on manufacturing cost in order to stay alive. And Cypress was one of those too. So we became the second, sort of in my mind, the second module maker that had affiliation with a chip manufacturer, if you will, and built off that know-how. And it was beautiful that the engineers at SunPower really embraced this. It really just gives me great joy thinking back on it, because at the time, if you're sort of come from more of a research background, manufacturing can be thought of as kind of turn the crank, crude thing, unlike solving Schrodinger's equation or something like that. So, but the reason that our engineers embraced it so much is that they intuitively understood this was needed and to succeed. And that was sort of the thing that brought everybody into this industry early on was this: we got to succeed, whatever it takes. The 1,000 people that came together in '73 to say, we're going to work on this. We're going to succeed. And our engineers had that same spirit. In fact, to such a degree that one of our engineers became the instructor for all of Cypress Semiconductor on statistical process control, SPC, and which is an arcane thing that's used in manufacturing. And he became the sort of local expert on it because he knew and we knew that we had to do this, right? This was to get the cost out of this thing. We had to become expert manufacturers. And so, of course, nowadays that's all kind of history. I mean, the manufacturing prowess has been brought to the industry as, manifold greater than it was at that point. But, Sharp was the leader at that time. In fact, they were the one we got And it was when Sharp started expanding capacity that really got Cypress said, okay, we got to go. These guys, they're expanding capacity. We got to go. And that's when we said, let's build the factory in the Philippines. And sort of Sharp was the vision on the hill that we followed at that time. Sharp was like the earliest module manufacturer too. So I think they produced the first commercially available solar panels. And in fact, our annual conference for the U.S. called Photovoltaic Specialist Conference came to Stanford in 1973, I think it was, around there. And I went. I didn't have anything to say because I was brand new, but I sort of watched to see what I was getting into. And I saw a presentation by Sharp on the current main market for panels, which was navigational aids and offshore oil platforms for remote power for those applications. And one of the biggest problems was that the Seagulls would come and leave droppings all over the panel, right? So this guy presented a panel on how by sticking pointed sharp wires all around the edge of the panel, you could keep the seagulls off. And I was watching and I said, wait, I'm going to devote the rest of my life to a subject where the main thing right now is poking seagulls in the butt. But Sharp, of course, was a major force in the early days of the industry.
Neat. Okay. Well, I don't know if you're running out of time now, but I've really enjoyed.
I'm retired. You're the one that's
okay. So I was also going to ask you too about, I know you're in Silicon Valley, and let's see, the beginning of Silicon Valley, you have Shockley and HP and things like that. And I used to live in Mountain View, and I think that's close to where you are, right where the Shockley Semiconductor, I guess that's pretty much where they invented Silicon Valley.
Yeah, right. Well, that history is, of course, well known, but it's, I ended up here by accident, really, as is almost everything that happened, in my life. It just sort of ended up here because I was very impressed with a textbook written by a Stanford professor that we used at Ohio State where I'd gone to school. The best written textbook I ever saw and encountered, and I thought, I got to go where this guy is.
All right.
And it said, looked in the cover, and I see Professor at Stanford. And I said, okay, that's great. Where's Stanford? So I applied here and was lucky to get in. And so I was plopped, that came in 1969. And so I sort of plopped down in the middle of this whole thing. And it was just by that accident that I ended up here, but it was certainly something in the sense that Intel had just been formed a year before. And so there was electricity in the air, if you will, about the transistors and that sort of thing. And the term Silicon Valley hadn't quite been, I'm not sure when that first arose, but shortly after that. But that whole history is, of course, well documented in lots of books. And in fact, one of the reasons I'm writing my current paper is that I noticed that the history of semiconductors tends to be written around the idea that they resulted in the transistor and the chip. And the idea that semiconductors could be solar cells, was pretty much ignored and thought of as kind of a sideshow, an irrelevant sideshow from the point of view of historical look at this. And because, all this early work in semiconductors like at Bell I was talking about blossomed into the chip industry and Fairchild and all of that. And then when I started looking more closely at it, I found that actually, the solar stuff was going right along with all of this. And many of the people that worked in the semiconductor industry also worked on solar cells, like I mentioned, Gerald Pearson, for example. And, but then that kind of got lost when the chip industry exploded into the huge, societal changing behemoth that it is today. But now, where the solar cell industry sales are, beginning to surpass the entire electronics industry, it's like this sort of ugly duckling that nobody wanted to talk about. It's just grown up into being a huge industry in its own right. So it's just kind of a fun twist, if you will, on the history of semiconductors.
Yeah, it's all different kinds of silicon and diodes. I guess you can call all of them diodes.
Yeah. In fact, when TJ, the CEO of Cypress, was pitching the idea of buying SunPower to his board, he had invested personally, but he was thinking of buying it. And he had done this at 2 board meetings and gotten told that you are out of your mind. And so, the third board, once a quarter, the third quarter, he's not going to let this one go, he's not going to let this one go by with the same result. So he put on a show that he invited me to it was unbelievable. There was hardly a dry eye in the house. He had sharp solar panels lined up behind him. He talked about how silicon, what Cypress does is they process silicon, and how, he had quite a dramatic flair. One of them was that he held up a 6-inch wafer at the time, the size of the wafers, and there was a memory, bunch of memory chips on there. And he asked his marketing guy, he says, "How much do we sell this wafer for?" And the marketing guy said, "I don't know, $600 or something, right? It's full of chips." And then he has a scale there, and he throws it on the scale, and he says to one of the board members, "How much does this wafer weigh?" And he looks at it and he says, "Well, it weighs, 0.8 ounces or something." "I don't know. I want it in troy ounces." And he figured out how much it weighed in troy ounces. And then he said, "How much that'd be worth if this wafer were gold?" And it was less than they sold the wafer for.
Uh-huh.
And they said, "That's it. We turn silicon into gold."
All right, there you go.
It was sort of the end of the meeting. It was like, okay, if you want your solar company, you can have your solar company.
Yeah, a little bit of alchemy there.
A little alchemy, yeah. But it paid off. I mean, I think that the height of, after we went public, we were some large fraction, like 80% of Cypress Semiconductor's market cap was the SunPower portion.
Oh, wow. Okay.
Yeah.
So the guy that brought you over to Stanford with writing the textbook, who was he and what's the book?
Oh, well, his name was Jim Gibbons, Professor Jim Gibbons. He became Dean of Engineering at one point. And actually, I owe him a lot, again, because it was he that sort of convinced Stanford to hire me as a professor. But he wrote a book called Semiconductor Electronics, and it was one of the early books on how transistors work and how you use them, because I was taking this course probably in 1965, and at that time, electrical engineering courses were centered around tubes for electronics, vacuum tubes. And so this was the first exposure that we had as students to transistors, and it just really felt exciting and the wave of the future. And the book was just so well written that it was written with the idea of explaining something to the student. I mean, that was clearly the entire motivation. So you want to know how a half-wave rectifier works? Here's how a half-wave rectifier works. Here's where you put the diodes, and we were so used to textbooks being sort of dry tomes full of equations or something. And so it was like a breath of fresh air. And I thought, gee, this guy's something. And so he was at Stanford, and he was working on, he had actually worked in conjunction with Shockley at Shockley Labs in the building you were just talking about in Mountain View, and was bringing, with the blessing of Shockley and the chairman of the department of Stanford, was bringing sort of the first semiconductor know-how into a university and creating a lab where students could do experiments on semiconductor and processing semiconductors. So that lab, evolved over the years and became the Center for Integrated Systems, which was a large, university-based research lab in chips, and the Stanford Nanostructures facility is what it's called today. But it was for a long time the most, and probably it still is certainly the most well-operated semiconductor university-based lab in the country. Now, there's one in Europe that is called the IMEC, the Interagency Microelectronics Consortium or something like that. It's sort of a European research lab that's far beyond what Stanford could do by themselves. So that when I decided to get into solar cells, processing silicon, and rather than amorphous silicon or copper oxide or cadmium sulfide and those sorts of things, was in that lab that we functioned and were able to make it. And when I realized I wanted to get into solar, I actually interviewed at several other universities, and it was in that process I realized, hey, the only place I can do this work that I want to do is at Stanford in the IC lab. I mean, sorry guys, but that's it.
Great. Good. Well, it's a lot of information here. I'm going to have to digest all of this for quite a while. I know, too, that we were talking a little bit about, about the Solar Roots movie that Jeff Spees made and some of those old timers there.
That Carl Bohr made, you mean?
Well, the documentary that's about how hippies started solar.
Oh, the hippies started solar. Yeah. Right.
And I guess you said you moved into the Bay Area in 1969. I guess that's...
69, yeah.
Yeah, 60. Are you a hippie? Were you then?
My hair got longer and longer the longer I stayed here. But I never, and I sort of, the whole movement with the, Joan Baez and the hippie encampments that were sprouting up like Struggle Mountain and the land were sort of, what's the right word? They were not aspirational. I'm trying to think of the right word. They just seemed really cool to me. But I was bound and determined to become a, research scientist in silicon. And, it's a little hard to live in the backwoods with a bunch of pigs running around. So,
I think the Grateful Dead started right there in Silicon Valley. I think.
Yeah. Absolutely. Yeah.
Palo
I
Alto.
think it was what's called. It was in Menlo Park. Well, I mean, they lived in Menlo Park, right near the Stanford campus, and then they performed at St. Michael's Alley and some of the restaurants and stuff in downtown Palo Alto. That's where.
Did you ever just walk into the pizza parlor and there they were playing?
No, I did years later. After I met my wife, and she was much more in tune with music, and we went to see Jerry Garcia play here and there and whatnot.
Great.
Yeah, I just didn't have time for that. I did, well.
And I also was just looking you up, too, and I saw that you're a sailor.
Yeah.
So I have a sailboat at Pier 39, if you ever want to go sailing.
Oh, okay. Right. I just took some people by there yesterday to show them the seals, and the seals were gone. There were a few, but it wasn't like I remembered when they had...
Yeah, they're still there. Maybe it's just a seasonal thing, or maybe there was some good fish in the bay. We went sailing a few days ago, and we saw some swimming in the bay. But not too long ago, they were all over the dock there, so maybe they just decided to go swimming. They have to hire a guy to keep them off the boats.
Well, yeah, and they discovered South Beach Marina, where I have a boat. They're kind of, it's sort of like nobody knows what to do with them, like... Can't shoot them. I mean, it's like, so
it brings a lot of tourists. I don't think that they want to get rid of them because
well, you're probably familiar with the sequence of events there, right?
It's easier for them to just hire a guy to chase them off the boats.
The boaters that were on that side of the harbor got the short end of that one because tourists like the seals better than the boats, but. I was on the sailing team in my undergraduate as a freshman, but then dropped off when I became more serious about engineering. But always had a warm spot for sailing. And then when we moved to California, I already had a young kid. So sailing a dinghy was not in the works. So we bought a Santana 22. I don't know if you know those boats. But
I remember looking at a Santana when I was boat shopping years ago. Yeah, I have a Ranger 33. Do you know that one?
Oh, okay. Yeah.
And it's kind of funny. I go to the post office, and Gary Moll is the guy that invented the Ranger. And his widow, his wife, is Shelley, and she waits on me at the post office.
Oh, really?
Yeah.
I didn't know.
And another... Did you know him?
Yeah. Gary Moll, no, but he designed the Santana 22 also.
Oh, I didn't realize that. Okay.
Yeah, that was his first design, and it's kind of put him on the path to the stardom that he did. And the Santana 22 was uniquely well designed for the bay. It was very stiff for a small boat like that, and could handle the winds and stuff. A lot of the similarly sized sailboats, like a Venture 22 with a swing keel, would just get killed on the bay.
Oh, yeah.
So
yeah, I couldn't imagine a 22-foot sailboat when it gets real windy out there.
yeah, and those antennas were, just plugging away. In fact, when I sold that boat, both my kids were. I found I was cleaning it out, and I found a harness for an infant. So when I ended up with the second young child, he would stay below in the Santana 22 with the harness on, so he wouldn't climb out. But it was a great boat. And then when Ranger started coming out, that was like aspirational for me. Like a Ranger 26, when that came out, it's like, oh man, that's the best. But I couldn't afford it, couldn't begin to afford it at the time. But so over the years, I had a bunch of sailboats. I eventually bought Express 27. Which I raced for 10 years or so. It was kind of a cult boat from Santa Cruz. It was an absolutely great boat. And it was designed by sort of a protege of Gary Moll.
Oh, great. Yeah, do you know about Wiley Cats, Tom Wiley? I don't know.
Sure.
Tom Wiley. He's one of my neighbors in a little town called Canyon. And
no kidding.
Yeah.
Oh, darn.
And it's like I've known him being around for a long time, but he eats lunch at the little community canyon school all the time like I do, so I get to see him all the time.
Oh, wow. Yeah. That's a small room. That goes into the small world. The boat that I was sort of know him for was the Wiley Rabbit, which became very popular, especially at Richmond Yacht Club. And there are a lot of Wiley Rabbits. A lot of them are still racing, and they're a trapeze keelboat of all things. But then, he went on to quite a career.
Great.
But all those guys, it's like Gary Ball died young, and then the guy that designed the Express 27, I did know him, and his name was Carl Schumacher, and he was just a fabulous guy, and he died young. So it's a good thing that Tom Wiley's still kicking. Glad to hear.
Yeah, maybe have you met him before?
No.
Of
course, I've seen his boats, including that big Wiley Catch. That's what's that? The ocean research vessel.
Yeah, it's like the Barrett or something like that. It's named after that winch. And it's funny. My other neighbor, he actually sails that one. He's like the captain of it. Or one of the.
No kidding.
Yeah.
Oh my God, you got quite a. That's good. I've never even heard of this area you're talking about. It sounds really interesting.
Yeah, Canyon. It's like 300 people in the redwoods, mostly off of dirt roads. So. And it's 1 mile east of Oakland.
Solar power, right?
Yeah, it's just like, it's an off-grid people that like their independence. And, my family came there a lot. We've had 7 generations out there now.
Jeez, that's amazing.
For California, it's kind of unusual. And everybody knows each other. And, my daughter goes to the school. And every day at lunch, it's open to the public, $5 for lunch. So, hey, if you want to come, I'll buy you lunch.
Okay. I can't believe I've lived here for 60 years or whatever it is, and I've never even heard of that.
Yeah. Well, it's a little town of 300 people, so not too many people have heard of it. In fact, some people, probably most of the people a mile away, never heard of it. Like, it's just right over the Oakland Hills, Montclair, between Montclair and Moraga.
Okay.
And just a little hidden town.
My goodness, that's...
unincorporated Contra Costa County, but yeah.
Oh, well, thanks for telling me about that. That's really something.
Yeah, great. Well, I really enjoyed talking to you, and I hope we can stay in touch, and maybe I'll invite you sailing someday.
What kind of boat do you have there?
Ranger 33.
Oh, the Ranger. I think you said that.
Yeah,
right.
And I could invite you too and see if Tom Wiley wants to go out also.
Yeah, that would be a hoot. So, right. Right. Okay.
Yeah. And what's your boat that you have now?
Oh, well, I've got two right now. I've got a Canard.
What was that again?
Canard, K-N-A-R.
Oh, okay. Canard.
It's a wooden boat, and a 30-foot wooden boat, which has a very active racing fleet here in the Bay Area, which I joined after I was racing. That's mostly what I did, was race sailboats. I didn't do sailboats much, but I raced a Express 27 and a J120 and a J111. and then decided to get out of that sort of big time campaign program type racing and joined the Canard fleet, which is unique in the Bay Area. It's a bunch of old guys and pretty much.
And a lot of varnish, probably.
Yeah, there's varnish, although all the boats have boat covers, but it's just got such a origin, a wonderful history that Canard does, and that it's a very special class. It was designed in Norway in 1943 and by a Norwegian, and it turns out that at that time, evolved a hobby amongst Norwegians of making a boat with the idea of escaping from the Nazis. And of course, Norway had a long history of boat building, but most of the boats they built early on were for raiding Europe, not for escaping from the Nazis. So this guy built this boat. It's not known whether that was his plan, but he got discovered, and the SS guy came and said, you can't do this. This is illegal. You can't build this boat. Of course, it was being built hidden in the woods, that kind of thing. And I said, oh, is that right? Oh, I'm so sorry. I'll tell you what. If you let me finish it, I'll give it to you. And the SS guy said, oh, yeah, hey, that sounds pretty good. I can buy that. So the SS guy let him finish this boat. And then he took it for a test run, and he didn't escape. He came back, and he told the Nazi guy, he said, unfortunately, this thing's a dog. I'm really sorry. And reportedly, he said, the boat is not suitable for the master race. I just think, in good conscience, give you this boat, And the Nazi guy goes, oh, well, okay, I don't want one not suitable for the master race. And said, I'll tell you what, I'll build you another one. So he did. He built another boat, which turned out to be the Canard, and just a sweet little 30-foot sailboat of that, looks like that era, like a little miniature 12-meter. But before he finished it, the Nazis all went home. So he's stuck with this boat, and people started liking it, and it grew into a big class of racing boats. The King of Norway has two, that kind of thing, and they have a world championship in Norway. It rotates around, but it's in Norway. The king participates, and he has the Marine marching band escort the sailors from the hotel to the marina with music. And, it's just quite a pageant. And I started hearing about this, and I thought, oh, wow, this sounds like a fun thing. But so I bought one at the beginning. It just when COVID hit, and it's very, difficult to sail. So I didn't do very well in the fleet, but part of it is that it's such a different kind of boat with a full keel or like a attached rudder to the keel. And partly because there's like 3 Olympic champions in the class, and it has evolved into probably, you could get arguments about this, but the most competitive sailboat racing in San Francisco. So then when I turned 80, I thought, I'm getting too old for this, so I'm trying to figure out what to do with it at this point. But,
and how old is the boat?
Well, my boat was built in 1961.
Okay.
Yeah, and in Norway. And it's towards the end of the wooden, but they switched. My boat's hull 107, and by 120 they had switched to fiberglass from wood, and they did everything they could to make fiberglass boats equal to the wood boats in terms of competitiveness, and they still compete. Fiberglass boats and wood boats compete against each other with no clear, distinction. You can't point to one being better than the other.
Yeah,
really.
I grew up with my dad liking wood boats and Chris Crafts and things like that. They were motorboats, but I used to have to work on them, and I've seen a lot of them rot away. So that's pretty good that you have one from the 60s that hasn't rotted away yet. So taking good care of it.
I mean, you look at it's unbelievable because it's planked, it's carbon planked, and you look at the outside of the hull and you cannot see any evidence of the seams. I mean, zero. I mean, these guys, they're just amazing. I don't know how, because they're beveled planks that are about 1.5 inches wide, where that bevel varies all along as it goes along the hull, from frame to frame. I mean, how do you do that?
And
I have no idea. I mean, it's just an incredible skill, but they're beautifully built. And I almost sank mine because I'd come off of the high performance, the J111s, and one of my crew who'd always been responsible for adjusting shroud tension says, I'm going to go the shroud's the tension. I thought, okay, fine. You're in charge of shroud tension. And we raced, and then I came back the next day to check things out, and the boat had sunk almost to the gunnels.
Oh, man.
And holy cow, and I started, got a bucket and I bailed it out, and it came, and if I had come a day later, it would have sunk clean down. And then I talked to him, well, you tighten the shrouds too much, imbecile, it's pulled the planks. It's like,
oh, man.
Jeez.
That must have been a lot of work fixing that.
Oh, man, yeah. So, they're a lot of work. They're not too bad because they're so well built, and they have we keep them, everyone has a cover on it, and so it keeps the sun off it.
You keep it in the water all the time?
Yeah, you have to keep it in the water pretty much, otherwise the planks shrink and sinks. So I have it at San Francisco Marina,
great,
along with almost all the other, because they don't have a motor, so to race it, you really have to be right there.
So you don't have a motor, you sail it to the dock?
Yeah.
Wow.
Yeah.
You have some.
Actually do have an electric outboard that is mountable on it, but it turns out it's kind of useless. So, yeah.
Well, you have some skills.
Well, I've been doing this since I was in college, so it's sort of been my hobby, I guess, would be the way to put it.
Great. All right. Well, thanks so much, Dick, for talking to me. Maybe we could do this again sometime.
Yeah, nice to know about your operation, and nice to meet you. And appreciate it very much. Appreciate your interest in the history of PV.
Yeah. Thank you so much. It's been great talking to you.
Great talking to you.
And thanks for changing the world and keeping it cool.
Well, I feel so lucky, to have helped move the rock a little bit. But I'll tell you, it's the people that came. I've never seen anything like it. The dedication of all the people that got together to do this.
All right. Thanks, Dick. Have a good day.
Okay.